joining in our first lecture. This is the linear algebra refresher. You can think of it kind of like a dictionary, where you learn all the important words and all the most important concepts in the language of mathematics that we're going to use throughout the course. So don't be too afraid now if it looks a little bit intimidating. Mathematics is actually quite easy if you know what you're doing. And I'm trying to explain it as much as I can. Also, please, I say this every time, but please do the homework. It's especially important for this lecture. The homework will give you better understanding of the concepts. It will, in a gentle way, make you engage with things that we do today. And sadly, there is no way around engagement with the topic. So if you really want to learn it, you have to put the effort into it. And the homework is not that hard. It might be intimidating, but if you don't know a word that you see, well, look it up in the dictionary. Mostly it will be as simple as that. Yeah, and don't worry too much about it. Okay, so let's start. Linear algebra deals with a thing, mostly, that we call the vector. Now, what is a vector? We define a vector as a thing that we can add. So we can add two vectors with each other, and we can multiply it with a real number. And in the context of vectors, we call the real number usually a scalar. So what are examples of that? Examples of a vector would be something that you already know, like arrows on the plane. And you can add those arrows. This here would be 1, 2 plus 1, 1. And you can also scale them with a real number. So you can multiply that vector here with 3, and it gets 3 times as long. You can also multiply it with -3, and you would get the vector that goes down here. But vectors are way more general, actually, than just those column vectors. For example, functions, real valued functions, are also vectors. So you can add two functions f of x plus g of x. You can also scale them with a real number, for example 2 times f of x plus g of x, and they behave just the same way. For when we have a set of vectors, usually we're interested in sets that have a specific property, sets that we call a linear space or a linear subspace or a vector space. and we call a set of vectors U a linear space, or if U is a subset of some superset, then it's a linear subspace. Exactly if, so by definition, exactly if, this double arrow means exactly if, and the two dots in front of it tell you that this is true by definition. Exactly if we pick two arbitrary elements from the set, we can add them and we can scale them with an arbitrary real number, and the result is still in the set U. So what would be an example for that? An example for U, for a linear space, is this line here, for example. When you take one vector, this one, and another one, this one, and you add them, you're still in the line. Also, you can scale them arbitrarily, and you never leave it. Oh, an interesting question. Can somebody name an element that is in every linear subspace, or in every linear space? Okay, it's the zero element, or the zero vector, because you can just take one vector and multiply it with zero. So you know that one must definitely be in any set that is a linear subspace. So basically, a linear subspace is closed under addition and scalar multiplication. Closed means no matter how you apply those operations, you never get something that is outside the set. When we have vectors, we can define a scalar product, and a scalar product gives us the notion of the length of a projection, with the length of a projection also a notion of a length, and also a notion of angles. So basically, when we have a linear space and some scalar product, we are endowed with the sense, with the basic notions of geometry. So now, if you think back to the fact that functions are also vectors, that means if you find a scalar product on functions, on real valued functions, you can calculate something like the length of a function, not in the sense of the length of the graph, but the length of the vector that this function is, and you can calculate the angle between two functions, or you can calculate the projection of one function on another. But what is a scalar product? Abstractly, a scalar product is a function that takes two vectors from some vector space U, some linear space U, and maps it to a real number, and it needs three properties. One of them is linearity. Linearity means here that we can decompose the sum, or a vector multiplied with a scalar, into the sum of the individual scalar products. we need symmetry. That means that we can switch the two arguments. So that means that the linearity also holds in the other argument. So we could have added something to C, or we could have scaled C with real number as well, and we would have the same properties. Some mathematicians that watch this video now might complain about the linearity. I try to keep the concepts in a way that we have a solid picture that is not too complicated inside the lecture. So the actual notion of a scalar product is a little bit more general than just with real numbers, but we're not going to use it. And everybody who's new to the concept, I don't want them to be too distracted by things that they don't actually need. This is not a mathematics lecture, even though it might seem, even though it might seem like one. I'm sorry. And finally, we need positive definiteness. And positive definiteness means that the scalar product of any vector with itself is 0 or greater than 0, so it is non-negative, and it is 0 exactly if the vector itself was already 0. So there's something that we call the standard scalar product. And that is how you might have seen scalar products in the past before, where you basically just multiply the two elements, pairwise elements of one vector with the other one, and then sum them up. So, for example, calculating the scalar product of these two vectors, would then be 1 times 2 plus 1 times 1 equals to 2 plus 1 equals to 3. But why does the scalar product give us a notion of projections and notion of angles? One can calculate, show proof by calculation that the standard scalar product actually gives you exactly the length of the projection of one vector on another. So there is one special case where this is quite easy to see, actually. And that is if we have two vectors from the unit circle. So note that we can, when we have two vectors, we can always look at them as if they were vectors in the real plane, because we can, let's say you have two vectors, right? This one and this one, and then you just consider the plane in which the two lie, the plane that is spanned by the two. And if you represent them in that plane, basically they look like vectors in 2D. And what happens now, we make another assumption. We think that one of the vectors is equal to 1, 0. And then if you have another vector, AB, then the projection And how do we calculate that? Well, it's just A, right? Which is our scalar product. And then this holds true in any case, actually. Can be shown by calculation, that is a little bit lengthy, so we're not going to do it in the lecture. And another thing that we can see from this here is that the scalar product, the standard scalar product, is equal to the length of the two vectors multiplied with cosine of the angle between them. Follows immediately here again from the interpretation in the unit circle. And with the standard scalar product, we can also define the L2 norm. That I have used already here. And the L2 norm is simply defined as the square root of the scalar product of the vector with itself. So what does it mean? It is just as if you calculated the length of the vector with the Pythagorean theorem. So when you plug that into this formula, you get x1 squared plus x2 squared and so on, and you take the square root of that, which gives you just the length of the vector. So one thing to note is that if you have a scalar product, you can also extend that, or if you can find a scalar product on a linear subspace, as I said, you have the whole notion of geometry. So you have a sense of length, of distance, you have a sense of direction, if something is in front of you or if something is behind you, and also a sense of orthogonality of angles. And we can define that and we can define that abstractly like that. If the scalar product between the two vectors is equal to 0, that means by definition that the vectors are orthogonal to each other. And we write that like that. And we can also define the orthogonal complement of a subspace. U orthogonal U orthogonal as the set of all vectors which are orthogonal on every vector that is in U. So for example, the 0 vector, or the set that contains just a 0 vector, would be, or the 0 vector is in the orthogonal complement of every linear subspace, and complement in the sense of it is complementary to this linear subspace. One can show that normally the subspace and its orthogonal complement span or yield the whole vector space. And with the scalar product, we also have a quick way of writing down something that we call a hyperplane. So a hyperplane in 3D would just be a two-dimensional plane that is somehow oriented in somehow lies in the three-dimensional space. In 2D, a hyperplane would be just a simple line. And in 1D, it's the point, but it also extends, that is the important thing, it extends into all vector spaces. So if you have 10-dimensional space, same concept, you have a 9-dimensional hyperplane in that space, but you can also think about hyperplanes now that we have scalar products. For example, if your linear space is a set of functions, so you can talk about hyperplanes in function spaces. And the hyperplane can easily be defined now. H is a subset of U, and it's a hyperplane exactly if there exists A and B A is a vector, B a real number, such that for all vectors in H, it holds that scalar product of the vector A with H is equal to B. And you can write H as the set X and U where scalar product of A with X is equal to B. With that, we can also introduce the concept of a linear function and of a matrix. And the function mapping from the vector space U to the vector space V is a linear function exactly if for every two arguments that we can take and every scalar that we choose, we can again decompose the function value of the sum into the sum of the function values. So that means if we have representation of some vector in that form, so if we write a vector as a sum of other vectors, we can write the function value as the sum or scaled sum of the function values of the individual vectors that we have. If we know that B and U, or let's like that, if we know that V is the Rn and U is the R. Let's say V is the Rm and U is the Rn. This is how we will usually write it. Then we can write the linear function as a matrix, and the matrix A can be written in this form, and it has all the properties of basically, because it is a linear function, it represents a linear function, and you can just write the evaluation at x, like usually as a matrix vector product, like that, and A times x can now be written in several different ways. So we can think about it as, we say, right, A as, it's column vectors as well, or we can write it in terms of its row vectors. So we can write A element-wise, like that. We can write it also in terms of its column vectors, and we can write it in terms of its row vectors. So the column vector, the first column vector would be A11 to AM1. The last column vector would be A1n to AMn. The first row vector would then be A11 to A1n, and so on. And with that, we can write the matrix vector product in a little bit different way. And that is as a weighted sum of the column vectors, but also as a new vector where each entry is a scalar product of x with the corresponding row vector. And we can a little bit quicker write the standard scalar product with the transpose. And we would get this expression. So this I'm telling you just because it is very useful. When you encounter a matrix vector product, sometimes you want to think about it as a sum of a weighted sum of the column vectors, or you might want to think about it as a list of projections of one vector on another. We also want to define the kernel and the image of a function. The kernel of a function is defined as all the elements in the original set that are mapped to 0. And the image of a function are all the possible function values you can get by plugging in the pre-images. So it might be noteworthy that when you consider the hyperplane again, do we still have it here? Yeah, we still have it. Every vector, you can consider a scalar product of a vector with A as a linear function, right? If you already fix one of the vectors, you basically get a linear function. And every vector, for example, that is orthogonal to A would be in the kernel of that function. So as an example, if we consider this function, the kernel of f would be, well, all vectors which are orthogonal to A, which give, when we put them into a scalar product with A, yield 0, which is by definition exactly the orthogonal complement. And the image would be all real numbers. Why is that? We can just choose x to be equal to A, as long as A was not equal to the 0 vector. And we can scale that arbitrarily, and this way you get all the real numbers. With these notions, we can also introduce the span of a set of vectors and a linear combination. And the span of a set of vectors is simply every possible weighted sum of the vectors in that set. So you can pick some real number for every vector, for every element in A, and you can multiply every vector then with its corresponding real number, and you add it up. So what are some examples of that? And just to say that any element in the span of A is a linear combination of the vectors in A, or is called a linear combination in A. So let's say our set A contains the two vectors 1, 0, and 0, 1. Now let's look up how it looks like. So we have those two vectors. And now let's see what is all in the span of those two vectors. So first of all, of course, we can pick for our second vector, lambda equals to 0. So that means we get all multiples of our first vector. The same way we get all multiples of our second vector. But we can also take any sum. So we can go, for example, we can go this far to the right, so scale or multiply the first vector with 2, and go up, add the second vector times 1, go up 1, and we land here. So this vector would also be in the span, correspondingly, because we can scale that again. All of this line is also in the span, and so on. So we can do that with this line, this line, this line, and so on. Basically, we find out that the whole plane would be the span here. If we, however, kicked out the second vector, A, just having one element, then our span would just be all the multiples of the first vector. When we have a linear subspace, we can, with a very mild assumption, the axiom of choice, find the basis of this linear subspace. So for your purposes, every linear subspace has a basis, and the basis allows us to write any element in the linear space as a linear combination of the basis vectors, as a unique linear combination of the basis vectors. So this sign means it exists exactly one, or it uniquely exists some lambda. Lambda would itself be some kind of vector. And we can write any element of U with its, as a specific, unique linear combination of the basis vectors. So for example, the set of the two unit vectors in R2 are a basis of R2. Because when we get any vector, let's say AB, we can only write it as A times 1, 0 plus B times 0, 1. There's no other way to represent AB as a linear combination of those two vectors. However, B bar would not be a basis, because you can, for example, express this vector either as 0 times 1, 0 plus 0 times 0, 1 plus 1 times 1, 1, or you could represent it as 1 times 1, 0 plus 1 times 0, 1 plus 0 times 1, 1, 1. So here the representation would not be unique, it is not a basis. Also, if B hat just containing 1, 0 wouldn't be a basis either, because you could not represent 0, 1. And usually, we can also write that here with B writing as a matrix. We can write U as a matrix vector product. We call the dimension of a vector space the size of the basis. Now, you might say, but wait a minute, I can pick there are different bases for one vector space, and that is true. So, for example, you could have kicked out this vector here, and B bar would have become a basis, and it would be a different basis than B. But one can show that no matter the choice of the basis, the size will always be the same for a given vector space. So it is actually well defined. And with hashtag B, we mean the number of elements in B. So a vector space can be infinite dimensional, and there are even vector spaces of different infinity, different infinite dimension, differently infinite dimension. A set of vectors is called linear dependent. Or independent. It's called linear dependent exactly if there exists a lambda unequal to 0 such that we can find a linear combination out of the elements in A that yields 0. Again, this set here would be linear dependent because we can write -1 times this plus -1 times this plus 1 times this. This would yield 0. However, the lambda would be -1 -1 1, so it would be unequal to 0. And we have found a linear combination of that yields the 0 vector. That is non-trivial. And conversely, A is linear independent if it is not linear dependent. Matrices, at least some matrices, have something that we call an eigenvector and an eigenvalue. A is a linear function, a matrix that takes a vector from the Rn and maps it to another vector in the Rn. And we say the vector x is an eigenvector to the eigenvalue lambda of A exactly if A times x is equal to lambda times x. So multiplying x with the matrix is the same as just scaling the vector with lambda, and the set of all eigenvalues of a matrix is its spectrum. And with this notion we can introduce the so-called spectral theorem, which tells us that a certain class of matrices has a very specific set of eigenvectors and eigenvalues. And that is if A times A transpose is equal to A transpose times A, which is the definition of saying that A is a normal, so-called normal matrix. We don't really need the concept of normality, it's enough to know that. Then there exists some matrix Q such that the transpose of Q inverts Q, so Q transpose times Q yields the identity matrix. And there exists a diagonal matrix B such that A can be written as the product of Q times D times Q transpose. And D will contain all the eigenvalues of A, and Q will contain all the eigenvectors of A. So one thing to note here is that this means that A, or the span of A, has an orthogonal basis of eigenvectors. That means we have a basis of the Rn that can be written, or that exists of, that is made out of the eigenvectors of A, and the eigenvectors of A are also orthogonal. Why is that? So if Q transpose Q is equal to the identity matrix, the scalar product between any two column vectors that are in Q that are not the same column vector, it will be 0. And it will be 1 exactly for exactly if we take the scalar product of the vector with itself. So that means we scaled the eigenvectors to unit length as well. And we can introduce the concept of symmetric positive semi-definiteness. And matrix mapping from Rn to Rn is symmetric, positive, semi-definite. Exactly if it is symmetric, that means A transpose is equal to A. And for all vectors that are unequal to the 0 vector, we know that the scalar product of A times x with x itself is, if it's semi-definite, greater or equal than 0, and if it is definite, it must be greater than 0. So that means that when you apply A to x, when you look at the image of x under A, it will still point in the same, roughly in the same direction as x itself. So when this is x, then A times x might be this, or it might be this, or it might be this, or this, but it will not point in the opposite way. With that, now, a simple corollary. So, the matrix is symmetric, and especially that it's symmetric positive semi-definite, then we can apply the spectral theorem, because obviously the matrix will then be normal. And that is quite an important property, because when we know that the matrix is, when we know that we can apply the spectral theorem, we know that we can look at the matrix completely in terms of its eigenvectors, of the basis of its eigenvectors. And if it's also positive definite or positive semi-definite, we know that all the eigenvalues must be greater or equal than 0, and they will be real numbers as well. And we can now use that for our first machine learning application, linear regression. The task in linear regression or linear approximation is to find a vector so that we have given matrix A, we have given a vector B, and we want to find a vector X such that we can minimize the distance between A times X and B. And this is the same as minimizing the square distance. And we can write that problem also in terms of the error that we call epsilon. We want to minimize the squared sum or the squared length of epsilon, or the sum of squared entries in epsilon, subject to the constraint that A times X plus epsilon has to be equal to B. So let's look at that. Normally, what we can see is this function is definitely differentiable, and what we usually do if we want to minimize something, we try to set the derivative to 0. We will look into that a little bit later in the next lecture, but we can do it right now already, and we can differentiate the function. We can set the derivative to 0, and maybe we can find out something. So let's see. First of all, by plugging in the definition, which is something that you should do normally. So when you do the homework and you have to prove something, maybe it is helpful to just plug in the definition first. We plugged in the definition, we expanded the term here in terms of basically a bunch of scalar products written as matrix vector products and vector-vector products. And we can now differentiate that. And set it to 0. and that gives us the differential of our error with respect to x is equal to 2 times a transpose a. X minus 2 times a transpose b. I made a little mistake. It is not the differential, it would be the gradient here. The differential, we would need to transpose the whole thing. And we want that to be equal to 0, which would then be equivalent to saying that a transpose a x is equal to a transpose b. And now there are a few things to note. So a transpose a is symmetric, right? It allows us to apply the spectral theorem, and also we can immediately see that it must be a positive semi-definite matrix. You can easily calculate that. And that means that the function that we have here is convex, so we can argue, we will see why that is the case in the next lecture, but we can already argue that when we calculate this, the solution to this equation, when we calculate the critical point, it must be an action to minimize it. And we call the equations that we get out of this the normal equations. Now, the question is, does an x solution to that equation even exist? And the answer is yes. Because the kernel of A transpose is equal to the image of A orthogonal. When you look at the homework, you will do proof of that. You can just apply the things you learned today in the lecture, substitute the things with their definitions, and the proof shouldn't be that hard. And you will see why this is actually enough for us. The homework and the tutorial, please. So we know at the solution x hat, it holds that A transpose A x hat is equal to A transpose B. So when we now plug in the solution the solution that we got from solving the normal equations, we have some error epsilon at x hat, and we can multiply that whole equation with a transpose from the left, and we get this equation basically, which is the same stuff but with a transpose to the left of it. However, because we know that x hat solves the normal equation, we know that a transpose times the error must actually be 0. So the error epsilon at least at the optimal solution is in the kernel of a transpose, and with this theorem here, we know that the error is in the orthogonal complement of the image of A. That means that the error is actually orthogonal to the column vectors in A. And that is quite an important statement because the assumptions that we made here were actually quite weak. One can extend this a little bit further, where you leave the Rn and you consider way more general linear spaces, and the result will still hold true. So it means that whenever you solve a problem where you that is of that form, a linear approximation, linear regression problem, then you know that the error will be orthogonal to the column vectors in your matrix. So you have an additional equation that you can use if you want to deduce the optimal solution. I want to talk a little bit as well about the applications of linear regression. So, for example, you want to fit a curve to measurements that you made. So you conducted some experiment. You have some x value that you measured or that you controlled, and from that you got out some y value that you measured. So it might be something like that. Your data points, if you draw them. And you want to fit a function that has the form and you want to fit a function that is parametrized by A, B, C, and D, and you can choose A, B, C, and D in such a way that the resulting function approximates your measurements as good as possible. And what does as good as possible mean? In this case, or by the way we chose our function, it means that we want to minimize the sum of squared errors. So when your function, that would be kind of a weird choice, but you can do it. Then you want to minimize r1 squared plus r2 squared plus r3 squared plus and so on. And the way you can do that is by constructing an appropriate matrix. So for A, we would have just constant 1, we could take just a constant 1. For B, we would take our first x value. For C, we would take the sign of our first x value. And for D,
the squared, x1 squared, sorry. And we do that for all of our m measurements. And we would multiply this matrix then with our weight vector at our arrow term, and that is supposed to yield y1 to ym. So with this very simple setup, you can solve the task of fitting a line to your data. However, there is one big assumption that we made, and the assumption is that the parameters that we fit, they have to be linear in the function. So here a does not appear as its square, or it does not appear inside some nonlinear function, but it is just a times something. It is just b times something. So you can choose what you multiply with b pretty much arbitrarily. It can be as complicated as you want. As long as b is not complicated, you can solve the problem by solving the normal equations. So usually if we have more measurements than we have parameters, then we have a unique solution. That is, if the features that we have here, so we call the columns would be the features. As long as the features are linear independent, as long as the vectors you get out of that are linear independent. Okay, so to understand that better and get better geometric understanding, I would really encourage you to go to the tutorial session to do the tutorial exercises. And for better understanding, to deepen it, you can just take a look at the homework and get a really, really sound understanding for the first lecture and a sound understanding of the concepts that we introduced today. So thank you very much for attending, and I hope to see you next week. Bye bye.